Hi, and welcome to the Constant Velocity Review. I'm assuming that you have finished the unit and you're studying for one of the outcomes. You can probably find in the description on the YouTube page how to download this file. The first page here is just a bit of a review. I'm not going to go over this, but you can take a look at it. It is a very quick summary. It's not meant to explain initially, but it's a good thing to take a look at it for a very quick summary. Let's proceed then to the first one, the constant velocity outcome number 1. So this was in your student tracker. The first part I want to go over in just a bit more detail. Given an position versus time graph, and that's what we have right here, you should be able to describe the motion, so that's in words, and in your description you should have the starting position, the direction of the motion, and the velocity. You should be able to draw a corresponding velocity versus time graph. You should be able to make a motion map and write a mathematical representation, also known as an equation, to describe the motion. So let's take a look at the first one. Okay, so it says here, well, we need to do a description. So we can say object 1. I think I need to go a little bit finer. Object 1 starts at the origin. You know what, I'm just going to pause and write it out so you don't have to watch me type. Okay, so I wrote that object 1. Here, object number 1 starts at the origin, here it is, and moves at a constant positive velocity. Object number 2, that'd be object number 2, starts at a positive position, so that'd be up here, and moves in a slow negative velocity. How do I know it's slow? Because the slope is not very steep at all. Okay, so the next part is I could make a velocity time graph. So for my velocity time graph for the object number 1, I guess it would be some type of fairly large positive value, and for number 2 it would be a smaller negative value. I'll just go like that. And for my motion map, I'll draw out my motion map in just a sec. So I'm going to do object number 1 in green here, and it starts at the origin here, and then it ends. And so my arrows, I think I'll do my velocity in red. I'll do that halfway, and we can see my velocity vector stays pretty constant. Next will be my object number 2, and I'll do object number 2 in blue. It starts at some positive place, maybe about over here, and it goes slowly to the negative, and it does not get all the way to the origin. So maybe I'll go over here. I have the same number of dots. I'm going to write here that here's where it starts, and then my arrows will be halfway, and you can see that constant negative velocity because it's going in the negative direction. For a mathematical representation, you know what, I'm gonna put some values in here. Let's say if this position here was at maybe 8, that this position here maybe was at 10, this position here is maybe about 6, and let's say that I don't know, 10 seconds went by. So for object number 1, let's do object number 1 in green. So if I think about my y is equal to kx plus b, my y value in this case is actually position. So I'm going to say the x, the position of here, is going to be equal to the slope. Well, the slope of this is it rises 10 and it runs 10, so it'd actually be 1 meter per second multiplied by the position, which is t, or sorry, the x-axis, which is t in seconds, plus 0. So I don't actually have to write the plus 0. So that would be an example of a mathematical representation for my object number 1. For object number 2, if I, again, start with my template of y equals mx plus b, again, the y is position, and I have to figure out what this slope here is. So let me just get rid of some of this clutter here. So the rise is -2. Again, the slope is rise over run. So in this case, the rise for object number 2, if it starts from 8 and ends at 6, it's going to be -2. And if it runs 10, it's going to be -2 over 10. So I could write this as a fraction of -1/5 or as a decimal of -0.2. I kind of like the fraction, so I'm going to go -1/5. And the units for that is meters per second multiplied by my time. But in this case, it actually does start at a position. In this case, it's 8 meters plus 8 meters. Okay, so there's an example. You have your turn coming up. You know what, just so that you can do the mathematical representation, I'm going to say again it goes from 0 to 10 seconds. I'll say it goes up here to, no, you know what, I'll give it, let's say it goes up to 20 meters. Here it goes much farther, and then this here maybe was 16. Okay, so I'd like you to give that a shot and do all the velocity versus time and the description and the motion maps and then the mathematical representation. So hit pause now and try the your turn. Okay, I hope you've completed your own work, because it really only is helpful if you try this first and then see, compare your answers. I wrote for object number 1, it starts at the origin and moves at a constant positive velocity. Object 2 starts at 16 meters from the origin and does not move. For my motion map, here I've got 1, 2, 3, 4, 5. I put 6 dots for green, and I notice I started at the origin and I'm moving it equally spaced away. The last dot, it can be your own choice about whether or not you put that arrow on it or not. We don't really know whether it's still moving at that point or whether it's going to go horizontal, so it's a bit of a judgment call. To be honest with you, I kind of like the arrow there. There's 6 dots here. You notice that I do the same number of dots because it's the same amount of time. One thing I forgot before too is for our motion maps, if we have numbers, we can put in how much time goes by. So in this case, 1, 2, 3, 4, 5. So I actually should say here delta t is equal to 2 seconds. I just thought of that. So if you think of, this would be t equals 0. Right, I'll just zoom in a bit. This would be t equals 2, t equals 4, 6, 8, 10. So this would stop at t equals 10 seconds. Oh, it's good I made that work. So each dot, 2 seconds goes by until I write the next dot. So that's why we have the right number of dots. For the mathematical representation, for object number 1, and I did it in green, x would be equal to 2 meters per second times time. Since the y-intercept was 0, since it started at the origin, we could write +0, but really you don't have to. For number 2, if you think about y is equal to kx plus b, and for object number 2, this slope was 0, so really that turns into 0, and you get x equals 16 meters. Okay, for the next part, this is still the same outcome. It's still CV1. Now, if we are given a VT graph, and here's what we have, we should be able to describe the motion of the object. We should be able to draw a position versus time graph, and we should be able to draw a motion map. Okay, so, well, I guess the first thing I'll do is we can describe it first, and here it's going 4 meters per second in the positive direction, and then it's going -3 in the negative direction, and then it's not moving at all. One thing that I have to say is that there's no information about where it starts. Okay, so I'm gonna just put in here, let's assume that the starting position, that's how we write starting position, is at the origin. In other words, it's 0 meters. Okay, so for my description, here I'll write it out and I'll just hit pause here. Okay, so I don't know, not too crazy. This first segment here is this segment here. The object moves in a positive direction at a constant 4 meters per second. And then this next section here is then the object reverses direction and moves in the negative direction at 3 meters per second. And then lastly, this section here, the velocity is 0. then it stops for 2 seconds. So that's how I'd write that. Now let's consider how we would write our xt. So we're going to start at the origin. Now here is the key here. Note area under, I'm going to put quotation marks around under, and you'll see why in a second, under the VT graph is equal to displacement, the change in x. So in other words, here I'll draw this in red, this rectangle here is what we're interested in. That's area number 1. So I'll do my calculations here. This area number 1 is equal to a length times a width. So this side here is going to be equal to 2 seconds multiplied by this height here, which is 4 meters per second. So what happens when we do 2 seconds multiplied by 4 meters per second? My seconds cancel out and I get 8 meters. Okay, so just to look at it again, if I am moving at 4 meters per second, so 4 meters per second is another way of saying it'll move 4 meters every second. And if that does this for 2 seconds, it makes sense that it's going to go 8 meters. So if it starts from 0, it's going to end up going 8 meters. Well, which we afterwards it's going to be going in the reverse direction. So I think if we count by ones, 1, 2, 3, 4, 5, 6. Oh, we have just enough room. 7, 8. So after how many seconds we have altogether? 5. 1, 2, 3, 4, 5. Okay, we'll just use this amount here. So after 2 seconds, it's all the way up to 8. Oh, tough one for me to freehand here, so let me try it. Oh, no. After 1, it's going to be 4, so try to do that nice. Okay, that's how that will look. So now the next segment will be, and this is why I say the area under the line, maybe it's best to say the area between the VT line and the x-axis. This will have an area of, now this side is 1 and this side is 3, so that will be 1 times 3 is 3 meters, and since it's below the line it will be -3. So here, maybe I'll just try to neat this up a little bit. This area here was plus 8 meters. This area here is minus 3 meters. So if I started from 0 and the change was plus 8, I went to 8. And now from 8, the change is minus 3. So I'm going to go down 1, 2, 3. And at 3 seconds, I'll be here. So I go down that amount. So I go from here down to there. Okay, it's too bad the time axes don't line up. Now I'm going to be motionless, so I just go like this. Okay, so from 0 to 2 seconds, delta x, the change in position was 8 meters. From 2 to 3 seconds, the change in position was minus 3 meters, and from 3 to 5 seconds, the change in position was 0 meters. So if it started at 0, it ended at 5. All right, now thinking about my motion map, I need to get up to 8 meters, so I'm going to say that this is, if that's 0, this would be 2, 1, 2, 3, 4, 5, 6, or I can go 7. There, I'll go like this. I'll go by ones. So this is 2 meters, 3, 4, this is 5 meters, 6, 7, this will be 8 meters there. And I'm going to put a dot every second. So my first dot will be at the origin. I'll put it underneath since I put stuff on the top. My 1 second later, I would be at 4. And then 1 more second later, I would be at 8. And since I'm going to be changing directions, I'm going to just drop down here. This arrow would go halfway. How fast am I going? I am going at 4 meters per second. So this is V. V equals 4 meters per second. Here again, I'm going at 4 meters per second. So 0 and then at 4 meters. Okay. Once I get to 8 now I'm going to be at 8, and a second later I will be over here at 5. And my length of this one will be halfway. Oh, I want red. Be halfway. And so my velocity here is equal to 3 meters per second, but in the other direction. And then at this point, t equals 0, 1, 2, 3. So this is t equals 3, and I keep on going here. T equals 4, 5, 6. How much do I go to? Oh, only up to 5. Let's just see my original graph. Yeah, I only go up to 5. So in fact, even on this one, it just goes up to 5 like that, and then it stops. So let's see. This one would be t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, t equals 5. So here's my start, and here's my end. There, it tells my story quite nicely. All right, so here is your turn. So if you can do the same things, I guess it's not clear to see, but we'll make this on the line at the end. So you get the same idea. It stops at the end for, you know what, let's not make it too much. Let's just make it go 5, 6, 7. So let's say it goes up to 8 here. Otherwise you have so many, you know what, change my plans. Let's go right up to 10, not to confuse anybody, like that. So there's that line there. And so let's see if you can do this, and please hit pause, give it a try, and then once you've done your best, then you can come back. Alright, so your answers might be a little bit different. Again, I went with the assumption that it started from the origin. My description I wrote slightly different. I said from t equals 0 to t equals 3 seconds, the object moves at a constant 3 meters per second. Then it changes direction because it goes from positive to negative and moves at negative 1 meters per second from t equals 3 up until t equals 7. From t equals 7 to t equals 10, it is stopped. Now, when I'm making my velocity time graph, I was thinking about, okay, my first interval, my first delta x, I got rid of my delta here by accident, so this is this area here, this first delta x, that would be equal to 3 meters per second multiplied by 3 seconds. So again, if it goes 3 meters for every second, and it does this for 3 seconds, 3 times 3 is 9. So if I assume it starts from the origin, then 0 plus 9 is 9, so it changes up to 9. Delta x2, now it's when it's moving in the negative direction. Here it's moving at negative 1 meters per second, and it does this for 4 seconds. So negative 1 times 4 is negative 4. So if it was at 9 and a minus 4 put together ends at 5. So that's why I end up at 5 over here. And then it stays at rest. You'll notice I had to cheat a little bit. My position versus time graph was not as friendly as I would have liked, so I just added 1. You may have changed the scale, and I'm sure your answer could be just as fine. So that's not really too important about whether or not you're going to extend your graph or work with it. So the motion map, I started at the origin. And then I went by jumps of 2. Oh, I should probably say delta t is equal to 1 second. So this would be t equals 1, and so on. It gets up to 9. When it gets up to 9, because I'm changing directions, that's why I drop my arrow, my dot down a little bit, goes the other direction, and then it goes until a stop. Okay, so I hope that was helpful. That's at the end of the CV1 assessment review.